And what we're going to actually do now is we're going to look at a very easy example and try to calculate this and show that it's not really that easy to figure out. So let's start off with this integral, right? So here we have f of x is equal to x squared. The lower limit is 1, the higher upper limit is 2, and our variable of integration is x. Okay, so what is this equal to? So here, let me get these out of the way actually. I'll put these here. So what is this equal to, right? This is equal to the limit as n goes to infinity of the sum of I from 0 of 1 to n of f of xi star delta xi. Okay, so let's break this down. First, let's figure out what delta xi is. Notice how here we're assuming that our intervals are all regular, which means every delta xi is going to be the same length. And if you remember from earlier, I talked about how this is equal to just b minus a over n. Well, so our b is 2, our a is 1, and we don't know our n, so we have this. So we know what our delta xi. Okay, so what is xi star? For this, remember, we have a choice. We can kind of do whatever we want, but it's nice to kind of stick to something. So without loss, like without a problem, we're just going to use the right-hand Riemann sum. So we're just going to look at the right-hand one. And so remember, when it's the right-hand one, this is just equal to xi. So it's almost like we can remove this star. We don't really need it. So what is xi star or xi? We're starting at 1. So it's 1 and then it's something. And since we're breaking up these intervals into little chunks that are 1 over n, right? We're going to do this I over n times. And so the way to kind of think about this, if you're a little lost, if I have some function and I start from 1 and 2 is like, say, all the way over here. So here I have 1 over n, 2 over n, 3 over n, dot, 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 dot. So this, the right-hand limit, right? So this is this is x1. This is x2. This is x3. So notice how this is 1. This is 1 plus 1 over n. This is 1 plus 2 over n, 1 plus 3 over n. So notice how these indices match up with the top. So this is kind of where I ended up getting this. And this is something you're going to have to think about when you solve a problem like this, right? And so let's make this into one fraction in order to make our lives easier. We're going to make this n over n. And here we get this is equal to n plus I over n. Okay, so now now we have xi star. So what is f of xi star? Well, we just plug it in. So we get f of n plus I over n. So our f, if we remember, is just x squared. So here we just take r squared. And so we get n plus I squared over n squared. And so this is just n squared plus 2ni plus I squared over n squared. Okay, so we're almost done. So now we can plug things in. So what do we have? We have the limit. Oops, I forgot the limit. Actually, I can do this just to the right. N goes to infinity of I equals 1 to n of n squared plus 2ni plus I squared over n squared times delta xi, which is 1 over n, right? So here we have f of xi star. And then here we have delta xi, right? So what do we end up getting? So here I'm going to have to use my summation rules, right? So these are the properties we learned back 2 lectures ago, so back on Monday. Or was it Wednesday? It might have been Wednesday. Yeah, Wednesday. And so what we have is the following. So here I'll break this down a little. So we get n squared plus 2ni plus I squared over n cubed. So here I can break this down into little chunks, right? N squared over n cubed plus 2ni over n cubed plus I squared over n cubed. Am I missing an n? No, that's okay. N cubed, right? Yeah, that's okay. So here we have from I equals 1 to n, I equals 1 to n. So limit as n goes to infinity. Here we have, I can bring out the n squared, right? Because in this case, we're summing over I. So there's no i's here, so the n's are constants for this little portion here. So in this part, n is constant. It doesn't get to be a variable until here. This is what makes n variable. So I can bring out the n over n cubed. Actually, I'm going to lower that. So I can cancel some of these, right? So I get 1 over n. And then I have the summation of 1, I equals 1 to n. Oh, this is something we've seen before, yeah? So this should be easily changeable. So here we can do the same thing. 2n over n cubed, that's just going to cancel out one of the n's. And then the summation of I equals 1 to n of I. This is another one we've seen before. And then finally, we can bring out this 1n cubed, and you get sum equals I equals 1 to n of I squared. And again, here's a third one we've seen before. So I can now just plug these in. And if I have enough room, I get 1 over n. This, if you remember, is just equal to n plus 2 over n squared times this, if you remember, is equal to n times n plus 1 over 2. And then here, finally, we have n times n plus 1 times 2n plus 1 over 6. So here, I'm going to work on the bottom, so pretend this doesn't exist for now. So this is equal to, so if you multiply these out and you cancel, what you're going to get is the limit as n goes to infinity of 1 plus, so this is the 1, right? Here we end up getting 1 plus 1 over n. So this is 1 plus 1 over n. I'm going over this a little bit fast just because there's no room for me to do it all. But you can try this out. So this is equal to this. So we have 1/3 plus 1 over 2n plus 1 over 6n squared. And so when we take these limits, this is going to go to 0. This is going to go to 0. This is going to go to 0, right? After I've distributed my limit. And so we get 1 plus 1 plus 1/3. So this is just 7/3. And this is what the area under the curve looks like. So as you can tell, this is freaking disgusting. This is not a very fun thing to do, right? I don't want to sit here doing these limits 6 million times and like using my summation properties, blah, 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 just to calculate the integral of some function, just to calculate the area. So now I'm going to pause for a second, let you think about this for a second, and then I'll keep going in like 20 seconds. This is a good time to, like, if you have any questions, I'll be on Discord. You can ask me or you can email me. Yeah. This would be so much easier in a big classroom. Oh well. Anyway, enough reminiscing about life before craziness. So as you can see, yeah, so this is disgusting. And the whole point of basically the rest of today and next week is to figure out how to make these nicer. And one thing we can do right off the bat is talk about properties of the definite integral. So this notation we call the definite integral. Did I mention that? I feel like I should have mentioned that somewhere. Where did I screw up? Or do I mention it later? I don't mention it later. Okay, so I should mention this now. For some reason, I don't mention this. This is called the definite integral. So this... Oops. Oh, whatever. It's red now. This is called the definite integral. So when I ask you to do a definite integral, this is what I'm asking you to do. Find the area under some curve, etc. So hopefully you don't need to use these big limits because what we're going to go over is some properties. So one of the properties we're going to go over, and here I can make this bigger. Sorry, I guess I should have made those other ones bigger. I don't know why I didn't. I'm an idiot. Sorry. I just realized this. Oh well. And so some of the properties we can do are these. And these are basically coming from our limits, right? So since we're using limits and we're using summations, we can do a lot of these things. And so one of the things we can do is here is we can change our variables. Change our variable of integration. The variable we use doesn't matter. I can use x, I can use t, I can use u, it doesn't matter. Even here, I can use other symbols. I can use c, I can use d. The letters, the numbers, whatever, they don't matter. And that's something we need to remember. Part 2, so here I should highlight these. We'll do this, yeah. That's okay. 2 is basically, if you look at it, we're taking the integral from a to a. So if you think about this for a second, we're taking the area of some function from some point to itself, which basically means we have no area. We're not really changing anything. So this is going to be 0. Okay, what's some other property? If I take some c, which is a constant, and I'm integrating, right? So this should just be, right? So if I look at this graph, c is just some line, right? That's the same color. Anyway, so c is some line. So if I take the area from a to b, well, this is just c times b minus a, right? And so this is where number 3 is coming from. Okay, so what's another thing we can do is I can look at opposite areas. So I can switch these areas here, and this is kind of weird, but I can look at things from the reverse side. And this is basically by manipulating delta x, right? So if I change this to, this is normally xi minus 1. But if I flip all of these intervals, right? If I have xi minus 1 minus xi, then this is just minus delta xi. So this is where this kind of minus sign is coming from. Some other things, if I have a constant, I can just pull it out. That doesn't change anything. If I have addition, I can just split them just like we've done with everything else. Derivatives, limits, summations, we can just always split them. And then part 7 is basically saying if I take the area from a to b, so if I take the area from a to b, and then I take the area from b to c, so here's c, it should be the same thing as taking the area from a to c. That was a horrible... From a to c, of f of x of dx. That's all this is saying. So these are 7 properties that we can already state about them. I'm not going to prove them because this is not a proofs class. But these are some nice things that we can do. So this is already things you should be able to prove if you wanted. But the really, really, really nice result, and something that's going to make it so we don't need limits and summations, is what's called the fundamental theorem of calculus.